So this question is a question solving systems of nonlinear equations. So the first thing I like to do with systems like this is to draw a picture of what each equation's graph might look like, and that will give me an idea of how many solutions I might have. So for the first equation, I've got y equals x squared plus 4x plus 4, which is a quadratic equation. And the graph of a quadratic is a parabola. And when I look at the leading coefficient of this parabola, it's a 1, which is positive. So I know the parabola is going to be facing up. The second equation is y equals negative x squared plus 10, which is also a quadratic. But this quadratic has a negative leading coefficient, so the parabola will be facing down. So I'm going to draw this up-facing and down-facing parabola in the same picture, and we might get something that crosses like this, where we would have two intersection points, and that would mean that we would have two solutions to this system. But the two parabolas might just touch each other like this. In that case, we would only have one solution to the system. Or these two parabolas might totally miss each other and we could get no solution for this system. So now I have an idea that I might have two, one, or no solutions. And I'm going to solve this system. And you can solve the system with substitution or elimination. So I notice that these equations are already solved for y. So the first step in the substitution method is done. So I am going to substitute the negative x squared plus 10 in for the y in the other equation. And that's going to give me the equation negative x squared plus 10 equals x squared plus 4x plus 4. And I'm going to move all the terms to the same side. So I'll add x squared to both sides. I'll subtract 10, and that gives 0 equals 2x squared plus 4x minus 6. So I have a quadratic equation, and I'm going to try to solve this with factoring. I'm going to factor the 2. And that would give x squared plus 2x minus 3. And I'll factor more. X times x would give me the x squared in the front. In the back, I have a 3. So 3 times 1 would give me 3. And I need a positive and a negative. And I chose to put the positive on the 3 and the negative on the 1 so that I could add to the correct middle term of 2. So now I've got it factored completely, and I'll use the zero product property and set each factor equal to 0. So I have x plus 3 equals 0, x minus 1 equals 0. That gives x equals negative 3 and x equals positive 1. And then I can find the y coordinates of these ordered pairs. So y is equal to negative x squared plus 10. And if x is negative 3, that gives y equals negative 3 squared plus 10. So negative times 9, negative 3 squared is 9. And negative 9 plus 10 is 1. So one of my solutions would be negative 3, 1. And then if x is equal to 1, I would have y equals negative 1 squared plus 10. That's negative 1 plus 10, which is 9. So the other solution would be 1, 9. So this system would have two solutions, negative 3, 1 and 1, 9. Solve the exponential equation by using the method of relating the bases. by first rewriting the equation in the form b to the u equals b to the v. And the equation that we're working with is 1 over the 5th root of 16 equals 2 to the x. So the method that we're using to solve this is to try to make it so there are the same base on both sides of the equation. Now the advantage of having it in that format is that exponential functions have this one-to-one property, and so it tells us that these exponents must be equal to each other. So when we simplify it to having the bases the same, then we can write that the exponents are equal to each other, and that's a much simpler equation. So in this example, I can see on the right-hand side I have a base of 2. So I'm going to start on the left-hand side working towards having a base of 2. I've got that number 16, and I know that 16 is the same thing as 2 to the, 4th power. So this is the same as 1 over the 5th root of 2 to the 4th power. And then we have this 5th root. And one of the things we need to keep in mind is that having roots is the same thing as having exponents. So if we have, say, the square root of x, that's the same thing as x to the 1/2 power. If we have the cube root of x, that's the same thing as x to the 1/3 power. So we have 1 over 2 to the 4/5. So because it's the 5th root, that's why I divide by 5 here. And then we have a property of negative exponents, which allows this base of 2 to be moved to the numerator. So on the left-hand side, we end up having 2 to the negative 4/5 equals 2 to the x. And now we have written this so that the bases are the same on both sides. The exponents must be equal to each other. Negative 4/5 is equal to x, and that is the solution to our exponential equation. A system of nonlinear equations is given. Sketch the graph of each equation and then determine the number of real solutions to the system. Do not solve the system. So in this example, we have the system of nonlinear equations, which is x squared minus y equals negative 2, and 2x minus y equals negative 6. And our goal in this question is to sketch the graph of each one of these equations and use that sketch to decide what is the number of solutions to the system. So let's start with the equation x squared minus y equals negative 2. It's easier for me to graph an equation if it's in y equals form. So I'm going to subtract x squared on both sides. That gives negative y equals negative x squared minus 2. And I'll divide by negative 1. And I have y equals x squared plus 2. So this is a quadratic equation. And in order to graph it, I'm going to get 3 ordered pairs. So I'm making a chart, and I'm going to choose x equal to negative 1, 0, and 1. You can choose any 3 x's you want. I have negative 1 squared plus 2, which is 3. 0 squared plus 2 is 2. And 1 squared plus 2 is 3. So that's giving me 3 ordered pairs that I'll use to sketch the graph of this parabola. I have negative 1, 3, 0, 2, and 1, 3. And my parabola looks something like this. So then the second equation is a linear equation, 2x minus y equals -6. I know it's linear because I have both x and y to the first power. And once again, so just like last time, we want to rewrite the equation in y equals form. So I'm going to subtract 2x, and we get -y equals -2x minus 6. I'll divide by -1, and I have y equals 2x plus 6. Now this equation is written in slope-intercept form. So it has a slope of 2, which I'll write as a fraction, that's 2 over 1, and a y-intercept of 6. So b is 6. So I'm going to find that y-intercept. 1, 2, 3, 4, 5, 6. And it has a slope of 2, so I'm going to rise 2 and run 1 to get to a second point on the graph, and then connect those 2 points with a straight line. I didn't really give myself a ton of room here, so I'm going to erase this table that I have. And if I erase this table, I can extend the lines that I stopped earlier. So I want to extend this parabola all the way and extend the line all the way. And the reason why that's important here is because if we want to know the number of solutions, we have to know how many intersection points we have. We have 2 intersection points. And so that's 2 real solutions. We want to solve the exponential equation 1.41 to the x equals square root of 2 to the 1 minus 3x. So this is an exponential equation because we have variables in the exponent. And there are 3 techniques, sort of standard techniques, for solving exponential equations that I always try to keep in my back pocket. And those methods are, number 1, to try to make the bases the same. Number 2, to convert to a log. And number 3, to take the log of both sides. Now, a lot of people will make the step to try to make the bases the same in this example. And that's because if you type square root of 2 in your calculator, you get something that is close to 1.41. It's close, but it's not exactly 1.41. So if we use the first method to make the bases the same, you will get an approximation for your answer, but not the exact answer. So I don't want to use that method. I don't want to do any estimating. I want to get the exact answer. So I'm going to skip that first method. Now I could also convert to a log and take the log of both sides on this one. And I can show you both of them, but I like taking the log of both sides better, so I'm going to do that one first. And the reason why I like to take the log of both sides is because I'm going to use natural log. And natural log is something that is usually easier to type in most calculators. And we want to type our answer in at the end into the calculator. So In that first one, we'll take the log of both sides. We're going to do natural log on the left. And natural log on the right. And then we're going to use the power rule for logarithms. We have x natural log of 1.41. 1 minus 3x times natural log square root of 2. And then I'm going to use the distributive property on the right-hand side. I'm going to distribute this natural log to both of these. So that's x natural log of 1.41 equals natural log square root of 2 minus 3x natural log square root of 2. And I want to start collecting the x's. So this term and this term have x's, and I want them on the same side of the equation. So I'm going to move this to the left. So that's going to give me x natural log of 1.41 plus 3x natural log square root of 2 equals natural log square root of 2. And now that I've collected the x's on one side, I can now factor out the x. And that will give natural log of 1.41 plus 3 natural log square root of 2 equals natural log square root of 2. Then I'm going to get x by itself by dividing by what's in the parentheses. And this is going to lead me to my solution. That's x equals natural log square root of 2 divided by natural log of 1.41 plus 3 natural log square root of 2. Let's type that in our calculator. Alright, so in my calculator I need to be careful with parentheses. In the denominator I've got multiple terms, so I need parentheses around the denominator to make sure that we divide by the whole denominator. So I'll do natural log, and I need square root of 2. Alright, let me delete that parenthesis. Alright, that now it's in the right place. So natural log square root of 2. I need parentheses around my denominator because there are multiple terms. Natural log of 1.41 plus 3 natural log square root of 2, and then close parenthesis for the log and close parenthesis for the denominator. So we've got approximately, how about let's round to 4 decimal places, 0.2505. So that's our exact answer here, and this is a rounded answer, which is approximate. Now, I mentioned that if we were to use that first method, making the bases the same, we would get an approximation. So let me show you that. So in this example, we have 1.41 to the x equals square root of 2 to the 1 minus 3x. So what I'm going to pretend like these two are the same number, the same base. They are very close to each other, but they're not exactly the same. But since they're close, we're going to go ahead and use the property. The property when you make the bases the same, if you have b to the u equals b to the v, you can say u equals v. So if we're saying those bases are the same, we can say that x is equal to 1 minus 3x. So the exponents are equal. So I would add 3x to both sides. That gives 4x equals 1. Divide by 4, x equals 1/4. And that is 0.25. So you can see that's really close to the right answer that we got earlier. And then finally, I'll show you how to do it with converting to a log. So let me rewrite the problem. And I have 1.41 to the x equals square root of 2 to the 1 minus 3x. And if I were to convert this to a log, I'm going to write the word log, and this log needs a base. So I'm going to use 1.41 as the base. Now the log always equals the exponent, so I'm going to use the exponent on that base. And then this other side of the equation is what goes inside the log. So square root of 2 to the 1 minus 3x power. So let's write this without all the colors. It's log with a base of 1.41, square root of 2 to the 1 minus 3x equals x. I'm going to use the power rule to move this out of the exponent. That's 1 minus 3x times log of 1.41 square root of 2 equals x. I'm going to use the distributive property. I'm distributing this log to both of these terms. That would give log of 1.41 square root of 2 minus 3x log of 1.41 square root of 2 equals x. And I want to collect the x's onto the same side. So I'm going to move this term to the right-hand side so I can have all the x's on the right. And that would give log of 1.41 square root of 2 equals x plus 3x log base 1.41 square root of 2. And now that I've collected those x's, I can factor out the x. I'm factoring out the common x, and that would leave 1 plus 3 log of 1.41 square root of 2. And I want to get x by itself by dividing by what's in the parentheses. And our final answer, x equals log of 1.41 square root of 2 over 1 plus 3 log of 1.41 square root of 2. So that's our exact solution by converting it to a log equation. So let's type that in the calculator and make sure we get the same answer that we got before. And as I said, I like the other method better, taking the log of both sides, because it's easier to type in the calculator. So here I have to go into a hidden menu, the math menu. I'm going to hit up to get to the bottom of the list. And we have this log base. So I can type a 1.41 square root of 2. I'm going to divide. I need parentheses around the denominator. That's 1 plus 3. And let me get that log in the hidden menu again. We have 1.41 square root of 2. And we'll close parenthesis for the denominator. All right, looks like my calculation is a little bit off. So it's, I can see where I typed it wrong. I typed 1.40 instead of 1.41. Let me do it one more time. And I can go back and just edit that one spot so I don't have to type the whole thing over again. There we go. Now we've got the exact same answer that we got with the taking the log of both sides method. Thank you for checking out my videos. Have a great day.